This lecture would explain you how to solve the numericals on vapor compression refrigeration cycle. Okay, and we would be dealing with a very simple case, simple numericals on vapor compression refrigeration cycle. I would just explain you the steps in solving such kind of numericals. So, a typical numerical of simple vapor compression cycle would involve the plotting of the cycle on a pH diagram. So this is a pressure enthalpy diagram where pressure is on the vertical, enthalpy is on the horizontal, and you would be given the condenser pressure and the evaporator pressure, or you would be given the condenser temperature or evaporator temperature. And because it is mentioned that it is a simple vapor compression cycle, so you need to plot this on the pH diagram for clarity before you actually get the properties. So the simple vapor compression cycle, this lower line would corresponding to the evaporator pressure or evaporator temperature, and the above line would correspond to the condenser pressure or condenser temperature. So let me call this inlet to the compressor as 1. You know that in the compressor, the process in the vapor compression cycle is isentropic, that is the entropy remains constant. So this is S is equal to C. And the pressure in the evaporator and condenser is constant, so this would be a horizontal line on a pressure enthalpy diagram. So the intersection of the condenser pressure line, which is this, with the constant entropy line, that intersection is 0.2. In a simple saturation cycle, the process ends on the saturation curve. So this would be 3. This is called as the F line. This is called as a G line. Okay, and the process of expansion in the vapor compression system is an isenthalpic process. So this is how it would appear to be. So this would be a vertical, and this would be your 0.4. Okay, so once you are given the condenser pressure or condenser temperature and evaporator pressure or evaporator temperature, you can construct the pressure enthalpy diagram like this. Now, how do you extract the properties? Now, suppose you are asked to find the specific refrigerating effect. Specific refrigerating effect. Now, what is specific refrigerating effect? Specific refrigerating effect means you need to calculate the enthalpy difference between 1 and 4. So H1 minus H4. Now, how do you find this specific refrigerating effect? For that, you need to find what is H1. Now, H1, if you look at 0.1, is the specific enthalpy at 0.1. Now, 1 is on the G line. So, we need to refer to the Hg value from the refrigeration tables. We need to refer to the Hg value from the refrigeration tables corresponding to the evaporator pressure or evaporator temperature. For example, if your evaporator temperature is 0 degree centigrade, evaporator temperature is 0 degree centigrade, then in that case, H1 would be Hg at 0 degree centigrade for the given refrigerant. Okay. So let us say that the refrigerant is R134a. So in that case, you need to refer to the R134a tables, go to the temperature tables at 0 degree centigrade and look for the Hg value at 0 degree centigrade. That would be your H1. Okay, so this is how you get H1. Now, how do you get H4? So for getting H4, we need to first find H3 because H3 is equal to H4. H4, you need to first find H3, right? And H4 is equal to H3. Now, how do you find H3? H3 is on the F line and the pressure is corresponding to the condenser pressure, the temperature is corresponding to the condenser temperature. Let us say that the condenser temperature is given to be 40 degrees centigrade. Okay, and then you need to find, if it is given as 40 degrees centigrade, then and it is on the F line, so you need to find HF value for finding this, HF value corresponding to 40 degrees centigrade. 40 degrees centigrade. Okay, once you get H3, that is equal to H4, and this is how you need to put these values so that you will get refrigerating effect. Its unit would be kilojoules per kg. Suppose you are given that the total capacity of the system is 10 tons. Now 10 tons is the total capacity. It means that 10 tons is equal to m dot into H1 minus H4, specific refrigerating effect into mass flow rate of the refrigerant. And 10 tons is nothing but 10 into 3.517 kilojoules per second. This is m dot into H1 minus H4. So you have found this H1 minus H4. You have found this values. Okay, you know this. So from that you can find m dot. So this is how you calculate the mass flow rate of the refrigerant if it is asked to calculate the mass flow rate of the refrigerant. Now supposing you are asked to find the coefficient of performance. Coefficient of performance. So coefficient of performance means what? Coefficient of performance means the enthalpy difference across the evaporator upon enthalpy difference across the compressor. Now this you have already found out. Enthalpy difference across the evaporator you have already found out. H1 minus H4 you have already found out. Now you want to find enthalpy difference across the compressor, that is H2 minus H1. For that you need to find H2. Now how to find H2? So for finding H2, what we need to do is that we need to equate the entropies at 1 and 2, and from that, after equating the entropies at 1 and 2, you get the temperature T2. And once you get the temperature T2, you can find H2 as H2 dash plus Cp T2 minus T2 dash. Now where is this 2 dash? This 2 dash is over here. Okay, 2 dash is over here. And how do you get this T2 from this? For finding this T2, S1 is G plus Cp ln T2 upon T2 dash. This expression has come from the entropy expression, and once you get this, you get T2. Once you get T2, you can find H2. Okay. So finding H2 is a bit difficult, but you need to do some practice for that. Okay, and once you get T2, you can find the enthalpy value H2. Once you get H2, then coefficient of performance would be refrigerating effect upon compressor work, which is H1 minus H4 upon H2 minus H1. Okay, so this is how we solve the numericals on vapor compression refrigeration cycle. This was a brief introduction. For a detailed solved problem on vapor compression, you can refer to my other video lecture. Thank you.